Alright everyone, so this is our last section of material, new material. We're going to cover a topic called the Binomial Theorem today. Kind of an interesting topic. It got some really neat mathematics involved, and so much stuff I wish I could cover in these videos, but it's not part of the course. But really, I would urge you to maybe do some external research on your own and look up some of the cool stuff that is kind of going on behind the scenes with the binomial theorem. When you get a chance, just in all the free time you have during this quarantine time. So anyway, before we get into the specifics of the binomial theorem and what it is, I'm just going to play a little game, have a little fun here for a minute. It does pertain to what we're talking about. What I want you to do or what we're going to do, and you can do this if you want at home, but I'm going to start with a triangle of numbers, okay? And I'm going to start with the number 1 on each of the 3 corners. Okay, so I have 2 rows essentially of 1s. Now from there I'm going to build a triangle with successive rows coming down, and each row is going to start with a 1, it's going to end with a 1, and in the middle we're going to use the sum of the 2 numbers above that location to give you a new number. Okay, and each row will have exactly 1 more number than the row above it. Okay, so the next row would start with a 1, it will end with a 1, and in between you have the sum of the 2 numbers above. 1 plus 1 equals 2. Okay, and if you continue that on, start with a 1, end with a 1, in between 1 plus 2 is 3, 2 plus 1 is 3. Right, again, then you throw a 1 in, a 1, and then you add again. 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. Okay, and we'll do one more for good measure here, and maybe we'll add to this as we go later. Throw the 1's in. 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5. Okay, and of course this could continue indefinitely. In fact, there's an infinite number of rows to this triangle, and it's a very interesting triangle. There's a lot of cool mathematics. In fact, it has a name. It's called Pascal a Pascal triangle, P-A-S-C-A-L. And the Pascal triangle is built this way and just has a lot of cool stuff going on. One thing you could do, one pattern you could do is if you were to just, if you were to extend this out, maybe 20-30 rows, and then just maybe do this on graph paper and shade in all the odd numbers, you get some really cool, you get a really neat pattern, a geometrical pattern. And there's other things. If you were to do a quick search on Pascal triangle, patterns in Pascal triangle, or something like that, you could find just a whole bunch of very neat things that go on, a lot of mathematics, a lot of sequences and things like that that are related to what we've seen in the last few sections. So stuff that I can't show you in this video would just take too long, but just really neat things. Anyway, back to Pascal triangle, how this is useful. So one thing is, if you were to take a binomial, okay, binomial is just a 2-term polynomial, like x plus y. Okay, that's a binomial. And if you were to start raising it to powers, like raise it to the 0 power, and then raise it to the 1 power, and then raise it to the 2 power, and so on, what you'll find is that there's a certain pattern in the coefficients of the terms. So first of all, think about this. Anything raised to the 0 power is simply 1, right? We don't have to do any work there. Anything raised to the 1 power is simply itself. We really don't have to do any work there. It's 1x plus 1y. I'll throw the 1's in there. Anything squared, binomial squared, is it times itself, right? So x plus y times x plus y. And if you distribute, you'll end up with x squared plus 2xy plus y squared. Okay. Of course, this is 1x squared and 1y squared. I'll stick the 1's in there again. And if you had something cubed, well, that is just itself multiplied 3 times. Okay. Now, if I were to expand that out, if you look at the first 2, that's the square. That's the one from before. And so you end up with x squared plus 2xy plus y squared times x plus y. And if I distribute this out, it's an x cubed, an x squared y. That is another 2x squared y. And a 2xy squared. Move that around, followed by an xy squared. Oops, xy squared, and a y cubed. Okay, so that gets us all of our terms, and if I combine all my like terms, I get x cubed, I get 3 x squared y's, I get 3 xy squares, and I get 1 y cubed, and of course that was 1x cubed. What I want you to notice is that there's a relationship between Pascal's triangle and the coefficients of these binomial terms, okay, or binomial powers really. And so first you have a 1, that's like the first row of Pascal's triangle. Then you have a pair of 1's, that's like the second row. Then when you square the binomial, you get the 1, 2, 1, which is the third row. And if you look at the third power, you get 1, 3, 3, 1, which is the fourth row, 1, 3, 3, 1. Okay? And so what's interesting is if you were to continue this pattern of raising a binomial to a power, the coefficients will match the corresponding row in Pascal's triangle. Now, the mathematics behind why that happens deals with this idea right here that every successive power is the previous one multiplied by xy, and when you multiply those out, it's like adding the 2 terms above in the triangle. Okay, that's how we got right here. We've got these 2 terms, the 1 and the 2, and the 2 and the 1 added together to give us our 3's. All right, and so that's how the triangle is built, and that's how these powers are built. And so without even really having to do all of this distributive property, I could just jump right to the answer if I wanted to raise, let's say, x plus y and raise it to a power of, let's say 5, right? So that's two down. That would follow this row of 1, 5, 10, 10, 5, 1. All right, so that would be 1x to the 5th. Now the degree, notice the degree of the polynomial has to match the degree here. So it's 1x to the 5th. It'll end in 1y to the 5th. And notice in between, so you've got your coefficients, 5, 10, 10, 5, 1 will be the coefficients going through. But notice the pattern in the powers of the variables. You start with x cubed here, and then it drops x squared, Oh, I'm sorry, pointing at the wrong one. X cubed, x squared, x, and then no x. And in the y's, it's the opposite. Starting on the right, it goes down, right? X cubed, y squared, y, and no y. And so same thing happens here. I would start with x to the fifth. That's got to be a fifth degree term. The next term, which has a 5 coefficient, would have one less on the x power, but one more on the y. And so you should always get a total in each term of the degree here. So, yeah, so here I got 4 and 1 make 5. Then you get the 10 on the next term, which drop the x1, raise the y1. Then you get another 10, drop the x1, raise the y1. Then you get a 5. I'm going to need a little more space. Oh, maybe not. 5, that'll be what? Drop the x1, raise the y1, and then finally a 1 on the last term, squeezing that in. Okay? So just some cool patterns show up here in these binomials. And so the binomial theorem itself is the idea that raising a binomial to a power will have coefficients that correspond to the rows in the binomial theorem. And what you need to notice is that the power on the binomial will pair up with the second number in the row. Okay, whoa, wasn't pointing at the right thing there. I was, but you couldn't see it. So the power in the binomial, the binomial raised to a power there, the powers will match up to the second number in each row of the Pascal triangle. Okay. Next video we'll do some examples of some more complicated, or just a variety of different types of binomials that you can raise to powers now.